Hi, I'm Nubis Kiar. I'm the creator of NubimQ, which is a highly available key value cache. It's pretty fast. Um, yeah, so today I'll be talking about a bunch of changes which we did, which uh, got us around 40% performance increase in throughput, which is, I think, a lot. Um, I'll start by going through our architecture, what it is, how it works. Um, so I'll get the other stuff, keep the other stuff for some other day. Let's go straight to the improvements which we did. So the key value pairs which we have, we store them in various shards. Each shard is responsible for a bunch of keys and stores their values. Um, let's talk about. So as we can see, there are two of these here. Each one, this is a diagram. In its current state, as you can see, we have a bunch of shards, and our engine, which is NubimQ engine, it auto scales up and down. It actually essentially predicts the traffic, and it predicts, okay, the keys are coming too fast. We need to increase the number of shards so that the per shard contention doesn't explode and our performance stays reliable and fast. And it does the same thing while downscaling as well, so that we are not wasting too much memory. Um, yeah, when there's not too much load per shard. So for each shard store, we have a bunch of shards and they auto scale up and down. So in the current state, these shards, they use currently something like sync.map, which is a standard. Let me just write down. It's a very standard thing in Golang. It's a part of the sync package. It essentially provided us a bunch of things like atomic updates and things like that. We didn't have to worry about these because we were doing a bunch of other things, how to scale up, scale down, when to resize and all. So it served its purpose for a while. But now that other things have matured a bit, now that our system is up and running, it is starting to show its age. Because sync.map is a very general thing, and you can't really scale it that much. Like there's a limit which you hit, and I was trying to hit that limit. So yeah, we need to change it. We need to change it. So there was this thing I came with. So there were a bunch of requirements actually. Let me explain them first. So whatever we were changing this with, I decided to go with the custom implementation of a hash table. I hope that didn't sound scary. So there were a bunch of requirements for this. So whatever we were going to make for this, we need to make sure that it had the same API, which is the two things, store and load, as sync.map, because since we're already using sync.map at a lot of places in our code, we didn't want to change all of them, of course. So it had to have the same API. This third one is an additional one. We must use traversal key value pairs because this one is useful while we were migrating keys from one store to another during migration. It must be fast, of course, because these things, they are the bread and butter of NubimQ. And if these are slow, there's not much we can do. Everything else, all this fancy worker pool, subscriber event and all, everything is useless because these things, they handle the actual load, actual reads and writes. They are the one responsible for that. So these need to be very fast because sync.map, it first of all takes a lot of memory. Second, the lock contention is pretty high. If the workload is read heavy, it is pretty fine, but when a lot of writes start coming in, the contention gets very high and throughput just goes to shit, essentially. So we need to change that. So yeah, it needs to be fast, and collisions are acceptable because I think I'll get to it in a while why they're acceptable. So this is what I designed for this. So there are three things. Let me just also write them here. There are three things in a design which are useful. Just make it bigger. Yeah, so we have three layers. First one is a hashing layer. Second one is number of some bunch of buckets, and I think chaining is fine. So hashing layer. So every hash table needs a hashing layer. What it does is some sort of key goes in. Let's say there's this key and it goes in our hashing layer. It hashes it. Now what generally happens right now in our current system, there's an indexer. It indexes the keys. This indexer essentially uses a polynomial rolling hash. It essentially traverses the whole key and gets its hash. So the reason it does this is because on this layer we want really good collision resistance, because of course it divides them among shards. So this one needs to be like almost bulletproof, uniform distribution, great. So it takes in let's say, also give an example here. Let's say there's a key A, B, C, D, E, F. So currently this layer, it takes into account each one of these A, B, C, D, E, F, G, H, however long it gets. So this layer currently depends on the length of string, and as the length of string increases, it also increases linearly. That's rate of time which takes. It is fine with this layer because each of the shard stores have their own indexer, so the load kind of gets distributed a bit there. So it doesn't really slow us down that much, and we also kind of need it because it divides them among these shards. So yeah, but the moment it gets in these shards, we don't need that level of distribution. So in my current design, what I've decided for custom shard is we'll keep the number of buckets fixed. Why? Because resizing slows us down, and our current design also ensures that our auto scaling design, which scales up, it's actually pretty smart in its own way. It makes sure that whenever the load per bucket, number of keys per bucket, gets too high, it just moves the writes to another shard store. So it essentially guarantees that none of the load per shard per these shards get too high. So we don't need a lot of guarantees which SyncMap provides. A lot of guarantees include resizing. Whenever number of buckets they get too congested, it essentially doubles the number of buckets. But we don't need that because the load just won't be that much per shard. So we can go with a very simple implementation, hashing layer. Let me just start with this hashing layer. So like I explained, this hashing layer, this one needs to be very fast because, like I said, this is the bread and butter of NuBIMQ. So how do we do it? One way to do it is some of the few things we want here. We want O of X, where X has nothing to do with N. And what is N? N is the length of our key. And where X is constant, it's constant as well. This is main thing because we need this essentially, because if it's not the case, otherwise we'll just be draining performance. And since the number of buckets is fixed in our implementation, we also making sure that in our custom implementation we are not resizing our buckets, because we don't need it. You can just give the number of buckets a good number, let's say something like 10 or 20 or something, and it would just work out pretty well because the load won't be that high. So hashing layer needs to be fast, and we can't make it fast if we are checking each one. So how do we do it? So essentially we need some sort of good balance between speed and collisions, because otherwise we could just take the first character like some dumb person, hash it and just do that. But of course that'd be pretty dumb. The distribution would be like very terrible. We'll have these things, a lot of load per bucket would get pretty high. Some there'll be some buckets will be like really hot, others won't be, others will be completely empty, which is just completely breaks the point of a hashing layer. And yeah, we also need separate chaining. For those who don't know, let me just walk you through this, why we need separate chaining. So let's say once the keys get hashed, they get assigned a bucket, essentially. But okay, cool. But since number of buckets is pretty low and constant, what if two keys get matched to the same bucket? How do we, take care of that one? So there's a way. It's called. It's a pretty standard way. It's called separate chaining. I think an image would be good. Yeah. So it's pretty. It's not that big brain. You just, if a bunch of keys get assigned to the same bucket, you just append them to this layer, and whenever you need to look for it, you just go through the same one. Let's say we have a get request for this key, we go through a hashing layer, we get the bucket, then we traverse this thing. Yeah, that's the thing. That's just what separate chaining is. It's nothing special, but of course this can slow things down if our hashing layer is totally trash, because we'll have some buckets which have a lot of things, and to look for them we might have to just go through the whole bucket, which is not good. So yeah, bunch of things. So what can we do here? One thing which can be very constant across things is that we can take the first value, mid value for each key, and the last value, do a bunch of mixing. What do I mean by that? There's a thing called bit mixing. It's a pretty standard thing among thing among hashes. It's a murmur hash. So what we do is we do a bunch of bit operations. So let's say from this thing, how can I type? Let's say from this I got the first value, the mid value, and the last value. We get the ASCII values, whatever they might be. Let's just call it X, this A is X, B, D is Y, and G is Z. And these are integers. Now, it might be fine to get a hash out of these by just XORing these together. But it won't be as well, because let's say this is a string. But this one, it doesn't takes into account their positions. For all we know, ADG, this might give the same hash as AGD or DAG. You get my point, right? So we can do a bunch of things here. One of these is bit mixing. This one, all this does is it takes into account the positions, just hashes them with a bunch of primes. Why primes? Because primes are good for mixing. You should read into it if you really want to know it. So yeah, essentially all our hash function does is takes the those three values, mixes them together for a nice avalanche effect. Okay, I should also explain that one. Now, what is avalanche effect? It's a thing in cryptography. Okay, one thing, a hash isn't cryptographically secure. We don't want it to be. But what avalanche effect is, that is for every small change, let's say for an XYZ, only X changes, then our resulting hash would be massively different, like totally different. And that's kind of the point of hashing. That's the avalanche effect. You can read about it. So this is a hash function, and because it's not depending on the length of the string, it is pretty fast and pretty consistent for any size of string. And like I said, I've set the number of buckets to 10, and for collisions I've used separate chaining. Yeah, these are things. Let me just show you the implementation pretty quick. These are some of the things. Custom map bucket size. Let me just explain the structs first. For the map, like I said, in our map, this is a custom shard. Probably should rename it to map. It has a bunch of buckets, and buckets are these. So it contains our buckets. And what are buckets? In each bucket, we have a bunch of entries. This is essentially a slice of entry and a mutex. Yeah, I think I should explain this one. Now, our custom map is a bit better than sync map in this way. It's because what happens in sync map is, right, let's say something gets hashed and then comes to the buckets. In sync map, the logs are bucket level. So let's say a key comes, it gets hashed, it needs to look into some of these. So what happens, right, when that key is being processed, this whole bucket is under lock. It's not even a read lock, it's actually a complete lock. So for those who don't know, there's a thing called mutex lock. So it means that it essentially ensures that at any given time only one key can access the bucket. I mean, it's probably fine. If they probably thought it was fine for the use case, it wasn't fine for my use case because it was slowing things down. And we want concurrent access to buckets. So what we've done is I've put locks on bucket level. So let's say whenever some key comes, it gets hashed. Let's say it gets hashed to this particular bucket or this one. So while that is being processed, only this particular bucket is under lock. And let's say at the same time some other key comes and gets assigned to this bucket. It can do it at the same time because they are separate things. And yeah, so it does adds to a little bit of overhead because this sync mutex, each is like something like 50 something kbs, but we're also making sure that the number of buckets we have, it's not even 10. Realistically, we are using something like 3 because our engine is pretty good, we can get away with it, and it's also pretty fast. So yeah, this is a thing. We have put a bunch of methods for it, like get custom map entries and all. This is the hash function, like I said. So we take the first 3 values, mix them. I should write it down. I should write things down more. Let's say mix stuff, and this one just uses avalanche effect, just so that we can have a pretty good distribution in the end. And yeah, these are our simple API, just like sync.map. This one loads stuff, we get the hash, we get the hash, we log down the particular bucket, and then we look for the key in its chains. Once we found the key, we return 2 things, that entry or whether it exists or not. Something similar for store. We've done this, we look for in the bucket. If it's already in the bucket, we update it. If it's not, then we append it. Pretty similar. And the get all, it just gets all the key value pairs from the bucket, so we can use it while migrating. Oh my god, the code is a mess, I need to clean it up. So we can use it while migrating. Yeah, so that was the thing. And yeah, what are the results of this? So I recently made this change, and it essentially led to around 4x increase, not 4x, 40% increase, which is like around 40% increase. So earlier, our peak throughput before doing this, it was 115,000 ops per second. I think I should have the old one somewhere. This is the new one. So as we can see in the old one, I think I should have the old one. Where's the old one? I'll attach it somewhere. So around the old one so the first half of these are the read operations, and the second half of it are the write operations, and in the middle it's a mix of both. That's just how our benchmark works here. So as you can see, our write operations, they are around 125,000 ops. Earlier it was like 100,000 ops. And around our reads also extremely fast. So there's a funny thing here. Sync.map is optimized for reads, and it is often said that if you have a read high workflow, that sync.map is a perfect thing. But our engine is doing pretty well here because even our custom implementation, which is not optimized for reads, is doing pretty well. So for our reads, we're getting 175,000 ops per second, which is okay. And yeah, these are some more conditions which we test them under. These are same. These are same for which we tested sync.map as well. Yeah. So this was it. Yeah. This is how I made NomeMQ 40% faster. I think it's pretty good on a 8-core machine without fans. And also mind that these Apple Silicon chips, they aren't really known for their multi-threading performance, multi-core performance. So yeah, that was the point of the video. I hope it was useful. I'll be continuing to make these updates, and if anyone wants to contribute, there's also contribute.md. Where is it? You should read it. If you're interested, you should try things out maybe. Issues and PRs are always respected. Thank you. That was it.